Welcome to this video series on optical spectra. Now, optical spectra played a vitally important role in the experimental proof of fundamental aspects of quantum mechanics. In lower grades, you learnt about the Bohr's model of the atom. And in this atom, the atom is modeled according to a planetary system, much the same as our solar system, where the positive nucleus is central to the atom. And that positive nucleus is made up of protons, which are positive, and neutrons, which are neutral. And the nucleus gives most of the mass to the atom. And then around the nucleus, just much the same as in a planetary system, there are electrons that are zipping around the nucleus in orbits. Now, this is according to Bohr's model, and these electrons occupy particular energy levels according to specific energy. So the electrons can't just have any energy. They have specific energies. The energy is quantized, and the electrons are found only in certain energy states according to the energies of the energy levels. So in this model, the electrons are moving or orbiting around the nucleus. And this is an approximation. Like all models, this is an approximation because it was later on shown that this model was actually not the whole truth, because it actually wouldn't have been stable. Because as you've already learnt, that if a charge is accelerating, as an electron would do if it is moving in a circular orbit, because it's changing its direction, it's changing its velocity, therefore it's accelerating. And if it's accelerating, it's going to give off electromagnetic radiation, lose energy, and then collapse inwards towards the nucleus. This doesn't happen. The electrons' positions are pretty stable. So this required that a more advanced model of the atom, the wave mechanical model or the quantum mechanical model, which involved orbitals, needed to be developed. But nonetheless, in this section, we are going to, in particular, look at the Bohr's model of the atom in order to explain atomic spectra. And one last thing I would like to mention to you is that there's a certain maximum number of electrons that can fit into a particular energy level according to Bohr's model of the atom. And the formula that is given is that if n is the primary quantum number, it's the number of the energy level, then the maximum number of electrons in a particular energy level is equal to 2 times the primary quantum number of that energy level squared. So for instance, in energy level 1, the primary quantum number is n equals 1. 2 times 1 squared is 2. Energy level 2, 2 times 2 squared is 2 times 4, which is 8. In energy level 3, 18. In energy level 4, 32. So the question it begs now is, this is all good and well, but what experimental proof was there for Bohr's model being partially correct enough in order for it to be taken seriously? And so this is where we look at a phenomenon called atomic spectra, and this video is about understanding emission and absorption spectra in more detail. In the video preceding this, we saw a demonstration by a scientist on how he used an incandescent light source to produce a continuous spectrum like this, and then he used a gas emission tube to produce emission spectrums that look like this. Now, this video's purpose is for us to go into greater detail in order to explain the theory behind this. But a continuous spectrum is something we kind of see in a rainbow. When we see this, we can think of what we see in a rainbow. We see the red and the orange and the yellow and the green and the blue and the indigo and the violet. Now, an incandescent light source would be something that doesn't burn. The word incandescent means not to burn. So, for instance, a light bulb doesn't burn as such. Sometimes we say it burns, but in actual fact it's not burning like, for instance, a piece of wood that's a light. So it would have a filament made up of a particular metal or combination of metals with a very high resistance, so that when you pass electricity through it, it gets so hot that it gives off light. Now that light would have all the visible parts of the spectrum in it, and therefore we call it a continuous spectrum. Now, an atomic emission spectrum is defined, and this is a definition that you need to know for your exams, is defined as follows. An atomic emission spectrum is formed when certain frequencies of electromagnetic radiation are emitted due to an atom's electrons making a transition from a higher energy state to a lower energy state. Now, we'll still explain this in more detail, but this spectrum is not continuous. It doesn't have all the colors of light. Something else we just need to note is that it talks about certain frequencies of electromagnetic radiation. Now, electromagnetic radiation, taking you back to grade 10, there's a spectrum that starts with radio waves and goes all the way through to gamma radiation. So most of electromagnetic radiation is actually not visible. So the theory we are going to delve into explains UV radiation, explains infrared radiation, as well as what it does for optical bands or optical lines that we are able to see. So when it comes to atomic absorption spectra, they are defined as follows. They are formed when certain frequencies of electromagnetic radiation that passes through a medium, example, a cold gas, is absorbed. So if you look at this emission spectrum, so here light is given out by the light source, but not all colors of light, only specific bands of light are given out, whereas here a continuous spectrum of light is missing certain bands of light. And if you look, you can see that the one is the negative of the other. So where the black bands are is where the colored bands are in an emission spectrum. So they are the inverses of each other. Now, these spectra are the experimental proof for certain aspects of Bohr's model that are valid. Let's quickly discuss the gas discharge tubes that are used in order to produce these emission spectra. Now, a gas discharge tube basically consists of a glass tube and with a anode and a cathode, two electrodes, which will be charged in a specific way by an external power supply. In this case here, the positive side of the battery would be connected to the electrode, which would be, we would call the anode, because it would be positive. And then the negative side of the power supply would be connected to this electrode, and this electrode would be negative. And so this would be the cathode. And here they represent the current as a conventional current. This is the flow of positive charge from the positive to the negative. And in doing that, it's going to excite the gas that is in here. So we talk about atomic spectra. So we are going to be working only with atoms of elements. We are going to be exciting atoms in a gaseous state of specific elements. So we will not be looking at, for instance, the spectra of carbon dioxide or the spectra of sulfur dioxide. We will not be looking at the gaseous forms of compounds, but only the gaseous forms of atoms, of elements. So the gas here would be, for instance, hydrogen or oxygen or nitrogen. And when this electrical current, this electrical energy passes through, it excites the electrons in the atoms of this particular gas. And then when those electrons fall back, they give off very specific photons of a specific frequency and of a specific color. So this links with what we learned in the photoelectric effect about the fact that photons each have a very specific energy. They have their energy is quantized. In other words, for instance, a red light has photons of a very specific energy and a very specific frequency. We are now going to delve into why photons have got very specific energies and very specific frequencies when you're dealing with a source of light that's only got one specific color. Now, when it comes to a gas that's being excited, the electrons that are excited, they behave in such a way as to produce various color photons, not necessarily only one color, and there's a reason for that which we'll soon enough find out about. So the first example we are going to look at is that of a hydrogen emission spectrum. Now, the hydrogen emission spectrum would be generated or created by placing an electric current through a gas discharge tube like this, which is filled with hydrogen gas. A very high voltage needs to be placed across this so that a high current can flow through here to excite the electrons in the atoms of hydrogen, so that the electrons will move to a higher energy level and then drop down and give off very specific colors of light, giving off photons with very specific frequencies. Now recall that the frequency of a photon is related to the color that is observed. So with a hydrogen emission spectrum, what is very interesting is that if you observe it by taking the light from here and then splitting it up using either a prism or using a diffraction grating like the scientist did in the video that preceded this, we then get the light coming from here, which as you can see has got a very specific color, being split up into its components. And it's not a continuous spectrum, it's a discrete spectrum, what we also refer to as a bright line spectrum, another name for an emission spectrum. Now, the values that you see here are the wavelength values in nanometers. And so I would like to encourage you to pause the video now and work out the energies of the photons of these different colors of light. And you can do this by using Planck's formula for the energy of a photon, E for the photon, equals Planck's constant times the frequency of light. And recall that frequency is equal to the speed of electromagnetic radiation divided by the wavelength. So if you take these two relationships and combine them, we get that the energy of a photon is equal to Planck's constant times the speed of light, or the speed of electromagnetic radiation, 3 times 10 to the 8 meters per second, divided by the wavelength of the specific electromagnetic radiation. And so using this relationship together with these specific wavelength values, you can work out the energies of the photons for these 4 different bands of visible light. So I've labeled each of these bands with A, B, C, and D, and I've explicitly shown the working out for band A. So the energy of the photons that are associated with that color band are equal to, or should I say the energies are equal to Planck's constant, 6,63 times 10 to the minus 34 joules seconds, times the speed of light, speed of all EMR in vacuum, 3 times 10 to the 8 meters per second. The wavelength for that band of light that we see on that emission spectrum is in nanometers, so it's 410 nanometers. Be very careful of units. So for the wavelength of the specific band of EMR, it's 410 times 10 to the minus 9 meters. 1 nanometer is 10 to the minus 9 meters. This gives us a very, very small energy of 4,85 times 10 to the minus 19 joules. But let's think about what this is the energy of. This is the energy of a tiny packet of light, a photon of that particular wavelength, of that particular frequency. So dividing by 1.6 times 10 to the minus 19 joules per electron volt, we get that the energy of the photons associated with that band of light will be 3,03 electron volts. Recall from our photoelectric effect module that in order to work with more comfortable energies, we can convert the tiny energies of photons into electron volts. So we go from joules to electron volts by dividing by 1.6 times 10 to the minus 19 joules per electron volt. That's the conversion factor between joules and electron volts. Now if we calculate band B, the energy of the photons associated with band B, then using 434 times 10 to the minus 9 meters for that wavelength, we get the energy of those photons is 4,58 times 10 to the minus 19 joules, and converting into electron volts, 2,86 electron volts. Doing the same for band C and band D, we get these values. And so we can see a pattern here. And the pattern is summarized as follows, is that as the wavelength of the bands increases, so the energies of the photons decrease. So we can see here that the wavelengths are increasing, and so the energies went from 3,03 electron volts per photon to 2,86 to 2,56 to 1,9 electron volts. So the energies of the photons decrease, but this makes sense because the energy of a photon is proportional, directly proportional to the frequency of the electromagnetic radiation. And we know that frequency is inversely proportional to the wavelength. So if the wavelength is increasing, then the frequency is going to decrease, and therefore the energy should be decreasing. So now the question is, we know about the energies of the photons. We can even calculate them. We can calculate the energies of the photons associated with these bands. But here's the big question. Why do those photons have those specific energies? And this is actually what this topic is all about. In order to answer this question, we need to first look at the energies of electrons in an atom. Now, if we consider an atom with an electron in it, like hydrogen, and this electron is in the lowest energy level 1, then if we were to supply energy to this electron by means of an electric current, as in a gas discharge tube, then what we would find is that this electron would jump up to higher energy levels and then would fall back down. Now, based on the conservation of energy, energy is not lost or created, but is merely transferred or transformed into another form. So if an electron were to jump from, after being excited, had to jump from here up into the 6th energy level. So it's now sitting here, and then it were to fall back down to energy level 2. What energy would be lost by the electron? Using this relationship here, where the change in energy of the electron is equal to the final energy of the electron minus the initial energy, we are going to answer that question. So we are going to look at the specific transition between energy level 6 and energy level 2. So I'm going to write it as follows. I'm going to say delta E 6 to 2. So this is going to be the initial energy here. This will be E initial, which is equal to 21,3 times 10 to the minus 19 joules. And then as the electron falls down, it is going to move down to a lower energy, and that's going to be E final, which will be 16,3 times 10 to the minus 19 joules. So this is going to be energy 2 for energy level 2, minus energy level 6. And remember that in an atom, when an electron is in a bound state, in other words, it's in the atom, it's being held by the nucleus of the atom, then electrons can only have specific energies. Those energies are quantized. In other words, for an electron in this particular atom, it can only be in energy levels that have those energies. So it cannot have an energy, for instance, of 18 times 10 to the minus 19 joules, because in an atom, in this atom, that 18 times 10 to the minus 19 joules is not allowed, because the electron can only be in specific energy levels with specific energy values. So for this transition from level 6 to level 2, we're going to work this out. Then the final energy level, or should I say the final energy of the electron, is going to be 16,3 times 10 to the minus 19 joules minus the initial energy of the electron, which was 21,3 times 10 to the minus 19 joules. And this equals minus 5,0 times 10 to the minus 19 joules. Now the reason it is negative is because of the fact that the electron is losing energy. So this implies, because it's a change in energy, this means it is a loss. So this is a loss of energy for the electron. Now, where does this energy go to? Well, that's the point. This energy can't just disappear. There's conservation of energy here. So we know that this energy jump from there to there, that came from an external source. And in a gas discharge tube, that would come from a highly energetic electron. So now we can account for that energy, but how do we account for the loss of the energy by the electron in dropping from energy level 6 to energy level 2? Well, that's where the photon of light comes in. This drop of energy results in an photon of a particular energy equal to this energy, 5,0 times 10 to the minus 19 joules. So the electron loses energy, but that loss of energy by the electron is now converted into the energy of a photon. And so this is how photons of light are actually created. When an excited electron falls down, it creates, to a lower energy level, it creates a photon. So therefore, using conservation of energy, we can say that the energy of the photon is equal to the magnitude of the energy lost by the electron when it drops from a higher energy state to a lower energy state. So this, to expand this would be E final minus E initial of the electron. So in this case, we could say that this photon has an energy of, and these lines represent absolute values, or they are the, you want to call it the magnitude function. So this, the minus sign then basically gets dropped because we are looking at the magnitude here. So it's 5,0 times 10 to the minus 19 joules. Now, using the formula for the energy of a photon, we can say that the Planck's constant times the frequency of the photon is equal to 5.0 times 10 to the minus 19 joules. And we know that Planck's constant is 6,63 times 10 to the minus 34 joules seconds. And that's multiplied by the frequency of the electromagnetic radiation that is carried by the photon. This equals 5,0 times 10 to the minus 19 joules. And so we're now going to divide Planck's constant on both sides, and we land up with the frequency of this electromagnetic radiation being 5.0 times 10 to the minus 19 joules divided by 6,63 times 10 to the minus 34 joules second, and therefore the frequency is 7,54 times 10 to the 14 hertz. Now, when we work with very big numbers, we work with certain prefixes, and we have already worked with M for mega, which is times 10 to the 6, G for giga, which is times 10 to the 9, and now big T for tera is times 10 to the 12. So that's the equivalent of a trillion. So we can convert this into terahertz by saying the following, that the frequency is 754 times 10 to the 12 hertz. So what we've done is we've moved the comma 2 places to the right, which means we've made this number bigger by a order of magnitude of 2, in other words by 10 to the 2. So we need to reduce this by 2 orders of magnitude, so we make that 10 to the 12. Now 10 to the 12 is the equivalent of terahertz, and so the frequency is equal to 754 terahertz. And this is synonymous with frequencies of electromagnetic radiation in the visible range. A few hundred terahertz is where you will find visible light on the electromagnetic spectrum. Now, we initially looked at the hydrogen spectrum, and we worked with the wavelengths of those bands of light that we found on the emission spectrum. So we do well now to look at what the wavelength would be of this particular frequency of electromagnetic radiation, visible light. So what we're going to do now is we're going to use the fact that the wavelength, or should I say the speed of light, is frequency times wavelength. That's the classical wave equation. And now we're going to divide by frequency on both sides. So the wavelength then is c over the frequency. And so the wavelength is 3 times 10 to the 8 meters per second. Divide that by the frequency. Now we are going to have to work with the frequency in hertz and not in terahertz. So we're going to do that. So it's going to be 754 times 10 to the 12 hertz. And this gives us a wavelength of 3,98 times 10 to the minus 7 meters. Now if we want to convert this into nanometers, then we need to move the decimal 2 positions to the right. So then lambda equals 398 times 10 to the minus 9 meters, because we've made this number bigger by 10 to the 2, so therefore we need to make this number smaller by 10 to the minus 2. So therefore lambda is equal to 398 nanometers. Now when we compare this value to the spectrum of the hydrogen atom that we saw previously in this video, we see that this value of 398 nanometers doesn't correspond to any of these bands on the emission spectrum. So the question is why? The answer is that those 4 bands are not the only 4 bands to be found on a hydrogen emission spectrum. And if we look at an expanded spectrum of the hydrogen atom, we see that to the left of the 410 nanometer band, there is a 397 nanometer band. And so our calculation corresponds to this band. It's out by 1 nanometer, which is a very tiny amount, so that is acceptable. Here's a very useful diagram that illustrates the different transitions that energized electrons can make when they drop down to lower energy levels. So when electrons in this atom drop from higher energy levels down to energy level 1, which is the ground state, then they give off photons that have a very low wavelength, but then obviously a very high frequency and a high energy. We can see the energy difference between the electrons here is higher than if an electron makes a transition from the same energy level but to energy level 2. So these transitions will produce photons that will be in the ultraviolet light part of the electromagnetic spectrum. That's known as the Lyman series. These transitions, referred to as the Balmer series, these transitions will produce photons that will fall into the visible light part of the spectrum. And then the transitions that end up in energy level 3, these transitions form part of what they call the Paschen series, and they are lower energy transitions, and therefore they produce lower energy photons, and these photons will be found in the infrared part of the electromagnetic spectrum. So this is really a very nice visual representation of the different series of transitions that we find in an atom when an electron drops from a higher state, higher energy level, to a lower state, a lower energy level. So before we end off this video, I would like to assign you some homework, and the homework states as follows: determine the energy of the photon, the frequency of the electromagnetic radiation that is associated with that photon in terahertz, and the associated wavelength of the electromagnetic radiation associated with that photon in nanometers, which is produced when an electron makes the following transitions in our hydrogen atom. So transition means it moves from a higher energy level to a lower energy level, hence giving off energy in the form of a photon. So I've asked here for you to make these calculations for each of these transitions. This will be from energy level 5 to energy level 3. So that would be part of the infrared series, the Passion series. And then do the same for the transition from energy level 5 to energy level 2. So it would be that transition there, which would form part of the visible light, the Balmer series. And then lastly, a transition from energy level 5 to energy level 1, which would be part of the Lyman series, and that would produce ultraviolet light. And we will look at the solutions to these problems in the next video in this video series.